Okay, hi guys, I am back. We're going to give this another try. If you were online with me just at the time I was supposed to start at 6 p.m, my apologies. I just have had a long day. There's been some difficult stuff to deal with and I just completely screwed up. Taken a minute to check my working. I'm ready to go again. This time hopefully without mistakes, but please help me out. If anybody does join and watch this live, pop it into the chat if you see something silly that I do along the way. I really don't trust my brain today. So let's get stuck in and just see how we go. Okay, so we've got the locus described by this situation here. Let me find my cursor. There we are. Okay, so we are dealing with modulus, and modulus means that we take the real parts and the imaginary parts, we square each bit, add them together and find the square root. So if we are doing the modulus of this thing, first of all we need to turn z into something where we can separate the real and the imaginary parts, and that's almost always the first step in solving loci questions. So if we put that into the left hand side, we'll have x plus iy minus 1 plus 2i, and on the right hand side x plus iy plus 1. Now we want to collect up the real parts like so, and the imaginary parts are here. So on the left hand side we'll have the square root of x minus 1 all squared plus 2 plus y all squared. We don't include the I when we're doing complex numbers, and my apologies, my phone is having a bit of a meltdown, says it's too hot, so I'm using that as a webcam. I don't think it's going to let me do that. And I don't have a way to cool it down quickly, so we will have to carry on without the webcam at the moment. Let's carry on. On the right hand side we've got x plus 1 all squared plus y squared. Okay, so then I can remove the square roots from both sides by squaring each side and expand the brackets. We will have x squared minus 2x plus 1 plus y squared plus 4y plus 4 is equal to x squared plus 2x plus 1 plus y squared. Now we can do a bit of cancelling through. We've got an x squared on each side, they cancel, a y squared here, the 1 on each side, and what we end up with is bringing everything to the left. We will have minus 4x plus 4y plus 4 is equal to 0. So minus x plus y plus 1 equals 0. So y is equal to x minus 1. The achieved point in this question was setting up this line here. And merit was the next bit of expanding and doing some simplifying there. Okay, I think I might be able to get the webcam going again. Let's try that. Okay. See if that works for us. Okay, it might conk out again if it gets too hot, so just bear with me if you do lose that little bit of video. Okay, differentiation. We have a cone. Inside of that cone we have a right-angled triangle sitting here like so. We want to maximize the volume of the cone. For that we will need to be able to do dv by dr or dv by dh. So we need to be able to represent the volume in terms of r or h, but as long as it's just one of them. Now the formula for the volume of a cone is on your formula sheet, and that is 1/3 pi r squared h. We can't differentiate that yet because we've got two variables, r and h. We need it to be in just one of them. So using the right-angled triangle we have there, we've got 20 squared equals h squared plus r squared. So we can rearrange to make h equal to, it would be 20 squared, which is 400. We'll take off the r squared, and then we square root it. So the volume is equal to 1/3 pi r squared times 400 minus r squared to the half. Okay, now if I want to differentiate that so that I can maximize it, we're differentiating with respect to r. We have, what have we got? We've got a product rule. So we have the first piece here of our product rule and the second piece here. So I'll start by differentiating the blue. That's 2/3 pi r squared. And we times it by the green without changing the green. And then we keep the blue as it is and we differentiate the green. So that will be 1/2 400 minus r squared to the minus 1/2 times by the derivative of the inside, which is minus 2r. Okay, now collecting that together, we have 2 pi r squared times the square root of 400 minus r squared all over 3. I've changed it into square root now because we're going to go on and solve it, and I find that a little easier to deal with. Let me just do that a little neater though. There we go. Plus, on this side, we've got the half cancels with the 2 there. The r comes out and multiplies by the pi r squared. So we have pi r cubed, 400 minus r squared to the minus 1/2 all over 3. But that 400 minus r squared to the minus 1/2, well, minus 1/2 is to square root it and put it on the bottom because it was a minus 1/2. Okay, so it's going to look like this. I'm going to rewrite it a bit better. So that would be all over 3 root 400 minus r squared. And one thing I've forgotten is the negative that was just here means we've got a negative there. We're going to set that equal to 0 to be able to find the maximum. So what that means is if I take this bit, this negative, bring it over here, it'll become a positive. So we'll be solving to find these two things equal to each other. I'm going to bring the denominators up and over to the left, to the other side, and multiply them. So we'll end up with 6 pi r squared times 400 minus r squared is equal to minus 3 pi r cubed. Wait, when I took it over to the other side, I forgot to take the negative off. There we go. So just going back a little bit, I took it, the minus bit that was in our subtraction over to the 0, but I was being a bit lazy with my writing and just deleted some things. So when we took that minus over, it becomes a positive, and I forgot to delete the negative on there. So that's what I'm doing. That's where I'm up to now. Okay, now if we divide through by 3, we'll end up with a 2 here. That pi cancels with that pi. Excuse me. And an r squared cancels on both sides. So we take an r squared out there, and we take 2 of them out there, that we just left with an r. Oh, one thing I forgot also, when I was bringing this one up to that side, to multiply it out, would multiply out the square root as well. So we are ending up with 2 times 400 is 800 minus 2r squared is equal to r. So now if we, what have I missed here? I have got something wrong somewhere. Oh, I've spotted it. Okay. Apologies. And if I make mistakes in the video, I'll let you know in the description to the video, so you can, if you're watching this back when it's after it's been recorded and uploaded. I made a mistake here. I forgot to reduce the power by 1. So this is just an r. that's just an r, and this over here was a singular r. Let's go back to this stage here. So when we cancelled through by r, we can only take 1 off of there, and it becomes an r squared. Okay, back on track now. This then becomes 800 is equal to 3r squared. So r will be 800 divided by 3, and then square root, square root our answer. The radius will need to be 16.3 centimetres. Now we have found when it happens. Now we need to find what that volume is. And so then volume is 1/3 pi r squared times 400 minus r squared square rooted. We had that from this bit just up here is where I'm looking to get that volume formula we worked out earlier. So then if I put 16.3 into that for the value of r, so we square that, and I'll do 1/3 times pi times that answer, which was r squared, times the square root, square root of 400 minus r squared, which we've got in there as an answer. And the volume is equal to 3,224.5 centimetres cubed. Okay, moving on to integration. Okay. So we have y is equal to the square root of px and y equals px squared. We need to find these points of intersection so we can integrate between them and find the area between these two curves. So for the points of intersection, we set those two equations to be equal to each other. So we need the root of px is equal to px squared. Square both sides, we get px is equal to p squared x to the 4. So p squared x to the 4 minus px is equal to 0. Take out a factor of px, and we've got x cubed p minus 1 is equal to 0. So either xp equals 0 or x cubed p minus 1 equals 0. Well, xp being 0 is this first point of intersection, so x equals 0 that we can see there, or x equals the cubed root of 1 over p by rearranging this bit. That's the same as writing 1 over the cubed root of p. And that is p to the minus 1/3. Okay, so this point of x right here is p to the negative 1/3. Okay, now our area is equal to the integral between 0 and p is negative 1/3. We want the top function, which is the square root function, so that is px square rooted. Take away the bottom function, which is the parabola, so that's the one we know is px squared dx. And working out what that's equal to, well, we have the square root of p times the square root of x. That is p to the half, x to the half. The x is the bit that we're integrating, so we raise that to the power of by 1, and we've got 3 over 2. We've still got p to the half, but we're now going to divide by the new power, which is the same as timesing it by 2 over 3. And then subtract the next bit we've got p is just a number, so it's only the x we're changing. Increase the power by 1, we get 3. Divide by the new power is 3. And the limits are 0 and p to the negative 1/3. Okay, that's equal to, now let's substitute in what we've got. We've got, in this one, p to the negative 1/3 to the power of 3 over 2 minus p to the negative 1/3 cubed over 3. And then we're going to subtract, substituting in a 0. Well, if we put 0 into those, we're just going to get 0. So that's helpful. Okay, now figuring out the algebra that's there. If we do powers of powers, those two things get multiplied. So that is, hold on, let me put that bracket back in. If we do 1/3 times 3 over 2, we get 1/2, and this one will be a negative one because it was actually a negative third, is 1/2. Now, if we do a power times a power, or the indices, those two things were times together. So p to the 1/2 times by p to the minus 1/2, we add the powers then. So 1/2 plus a negative 1/2 is going to cancel out, and we end up with p to the 0, which is actually 1. So we've got 2/3. Right, next one, bear with me. P to the negative third times 3 is p to the 1. We've got a p to the 1 here, so p to the 1 times p to the negative 1, again, is p to the 0, because 1 plus minus 1 is 0. So that's just 1, because anything to the power of 0 is 1. So 2/3 minus 1/3 is equal to 1/3, exactly how we wanted in the question. Oh, I didn't tell you where the achieveds and merits were on each of these, so I'll just quickly do that. In this integration question, there was just one spot to get a merit, and that was by doing this line here, doing the correct integration. On the differentiation, let's just pop back to that one. The achieved, if you got, okay, so you could get an achieved, it's hard to describe, if V was a little bit wrong. So a little wrong, but you integrated it correctly. Sorry, differentiated correctly. So differentiate correctly. Now, if you got V correct and you differentiated correctly, then you get the merit point at this line. And then obviously excellence for all the way through. Where was complex? Oh, I did go over the complex one for you. Okay, so apologies for anybody who's watching this back afterwards. And I've lost the webcam again. Those who came on the live at the right time, and I just had a little bit of a mathematical meltdown on that one, unable to spot my mistakes. So apologies if you're needing to watch this back at another time, because I screwed up that live. Hopefully this was helpful to you, and I will see you again for another one. We've got just a couple more left before the exam for this year's round.